Hello everyone, a very warm welcome to all of you. In previous class, we learned about the types of radiation, stimulated absorption, spontaneous emission, stimulated emission, and laser action. Now today, we will learn about Einstein lasers Einstein coefficient. Lasers Einstein coefficient means it provides the necessary condition to have a laser light. Einstein coefficient, it provides the necessary condition to have laser light. And we know that with the help of stimulated emission, one can have a laser light. That is, we can emit the light in a particular direction with the help of stimulated emission. So before understanding the Einstein coefficient, we need to understand, means we need to recall all the radiation. First we have stimulated absorption. If we have two energy levels, E2, E1, having N2 be the number of electrons in energy level E2 and N1 be the number of electrons in energy level N1. If we supply some energy, rho nu, say rho nu, to the electron in the energy level E1, then the electron in the E1 will goes to the excited state to the E2. Means there is a transition of the electron from the level E1 to E2 when we supply some energy rho nu due to the absorption of energy. Means the electron will absorb the energy and transit to the level E1 to E2 during during the supply of energy. So this is known as stimulated absorption. So the stimulated absorption depends on the two factor. Here the rho nu is equal to the E2 minus E1, means the energy difference between the two levels. Stimulated absorption depends on two factor. The two factor is as it supplies some energy. So it will directly proportional or depends on rho nu as it supplies some energy to the level E1. So E1 means it will depends on the number of electrons in the energy level E1. In the energy level E1, so which is N1. So directly proportional to N1. So since there is a transition from the level 1 to 2, so we will instead of writing the proportionality constant, we will write it as B1 2, means transition from 1 to 2 depends on the number of electrons in the N1 level rho nu, energy rho nu. Then we have spontaneous emission. Again we have two energy level E1, E2, N2 be the number of electrons and N1 be the number of electrons respectively on E1 level and E2 level. Spontaneous, it occurs naturally. There is no need to supply an extra source of energy, rho nu or anything. So the electron in the level E2 will transit to the level E1 and it will emit some energy in the form of photon. One thing, spontaneous emission, it occurs naturally. So this is all about spontaneous emission. Again, in spontaneous emission, we need to observe, and we observe that it here it does not depend, here it occurs as it occurs naturally, so it does not depend upon the extra source of energy. It only depends upon the number of electrons in the energy level E2, means it depends on N2. So it is directly proportional to N2, and we will write it as, since there is a transition from the level 2 to 1 to 1 and 2. Third, we have stimulated emission. We have two energy level, E2, E1. In this case, instead of supplying energy to the to the level E1 as we did in stimulated absorption, here if we supply energy rho nu to the level E2, electrons in the level E2, then there will be a transition, and during transition it will emit some energy in the form of two identical photons. Two identical photons. Here, in stimulated emission, it depends on two factors. First, how much energy we supply. So this is rho nu, directly proportional to rho nu, and how much electrons are available in the energy level E2 means number of electrons available in the E2 level, N2. So this is, and since there is a transition from 2 to 1, 2, 1, N2, rho nu. These are all about for the calculation purpose for Einstein coefficient. Now we will move on to the calculation part for the Einstein coefficient. So these are all about radiation, and to have a good laser we have some necessary condition, and these necessary conditions are nothing but Einstein coefficient. Einstein coefficient provides the necessary condition to have a laser light. So we have this condition. Now at equilibrium, we see that this is a upward transition, this is a downward transition, and this is a downward transition. At equilibrium, the number of the upward transition is equal to the number of the downward transition. So number of upward transition is equal to number of downward transition. So B12 N1 rho nu plus A21 N2 plus B21 N2 rho nu. So separating rho nu, we get A21 N2 divided by B12 N1 minus B21 N2. Dividing the numerator and denominator by B21 N2, we get A21 N2 by B21 N2, B12 N1 minus B21 N2 divided by B21 N2, we get A21 B21 B12 B21 N1 by N2 minus 1, which is rho nu. Say or call this as equation 1. Now again, by using Boltzmann distribution law, we know that the number of the availability of the electron at any energy level can be written as Ni equals to N naught e to the power minus Ei by kT. Means by using Boltzmann distribution law, the number of availability of electron at any energy level can be written as Ni be the number of electrons in the ith level equals to N naught e to the power minus Ei by kT. If we want to calculate for the energy level 1 or energy level 2, we will get N1 equals to N naught e to the power minus E1 by kT, and N2 equals to N naught e to the power minus E2 by kT. From this we get N1 by N2 equals to n naught will cancel out. We get E2 minus E1 by kT. E2 minus E1, energy difference between the two levels is what? Obviously h nu. So h nu by kT, n1 by n2. One thing we get, call this as equation 2. Now what we can do? We can substitute the value in equation 2 in equation 1. N1 by N2. We will put the value of N1 by N2 in equation 1. So rho nu equals to A21 B21 divided by B12 B21 N1 by N2 minus 1. We'll put the value of N1 and N2 from equation 2 here. N2 B21 by B21 e to the power h nu by kT minus 1, just rho nu. Call this as equation 3. Now again, according to the Planck's radiation law, the amount of energy that anybody is emitting can be written as rho nu equals to h pi. Okay, I'll write this now. According to the Planck's radiation law, Planck's radiation law, the amount of energy that any body is emitting can be written as rho nu equals to h pi h rho cube by c cube 1 by e h nu by kT minus 1, where rho is the amount of frequency of the nu is the amount of frequency of the emitted radiation, c is the speed of the light or velocity of the light, k is the Boltzmann constant, and T is the room temperature or temperature. Now call this as equation 4. Now can we compare equation 4 and 3? Yeah, compare equation 3 and 4. Comparing 3 and 4, we get A21 by B21 equals to 8 pi h nu cube by c cube, and B12 by B21, as it multiplies with some 1, so B12 by B21 equals to 1. These are two Einstein equation in laser, Einstein coefficient in laser. Now what we can derive from the from here, now we will derive some necessary conditions from these two equations, and these necessary conditions are called the Einstein coefficient to produce the laser light. Now R equals to spontaneous emission and the ratio of spontaneous emission by stimulated emission. So R equals to spontaneous emission A21 N2 and stimulated B21 N2 rho nu. We get spontaneous emission A21 and stimulated emission B21. Now we know rho nu equals to 8 pi h nu cube c cube 1 by e h nu by kT minus 1. Okay, then replace this by this. we get E h nu by kt minus 1 equals to 8 pi h nu cube c cube into 1 by rho. 8 pi h nu cube by c cube is what? A21 by B21, which is Einstein. These two are the Einstein coefficient, and we need to remember these two equations because these two are the basic. So A21 by B21 equals to 8 pi h nu cube by c cube. Substitute the value of this, then we get E h nu by kt minus 1 equals to A21 by B21 1 by rho nu. N2 N2. Substitute the value of A21 by B21 rho nu. We get R equals to E h nu by kt minus 1. So, from this equation, we observe that at high temperature and low frequency, under this condition, high temperature and low frequency, R will be greater than A21 will be greater than B21. A21 greater than B21 means spontaneous emission dominates the stimulated emission. But to have a laser light, we know that stimulated emission should be greater than spontaneous emission. Means B21, A21 should be less than B21 to have a laser light. Here, spontaneous emission dominates the stimulated emission. But to have a good laser light, but to have a good laser light, which is a necessary condition, stimulated emission should be greater than spontaneous emission. So, if here R equals to A21 by B21 1 by rho nu. So, if rho nu is high, then R will be less. If we increase rho nu, if rho nu is high, then R will be less. If R will be less, then A21 will be less than B21, which we get that the necessary condition. Means the spontaneous emission is greater than the stimulated emission. Stimulated emission is greater than the spontaneous emission. Rho nu, which is the input energy. That is, by this, we understand that input radiation should be high, which is the first necessary condition. Input radiation should be high, that is rho nu is the input radiation. If the rho nu is high, then R will be less. If R will be less, then A21 will be less than B21. B21 is the stimulated emission, means stimulated emission is greater than spontaneous emission, which we get the necessary condition to have a laser light. A bit confusion bit created, but if you means understand the concept, then it will be obviously clear. So the first condition is that the input radiation should be high. Now to create the second condition, we will move on that to the ratio of stimulated emission to the stimulated absorption. So which is B21 N2 rho nu is ratio of B1 to N1 rho nu. Since we know that the Einstein coefficient B21 by B12 equals to 1, so N2 by N1 is less than 1, means N2 is less than N1. Why I said so? If we take energy level E2 and E1, N2, N1, whatever the electron that is present in the ground state, all the electron will never excite to the excited state. Based on the supply of energy, only a few will absorb the energy and excite to the energy level E2. So N2 is less than N1. But to have a stimulated emission, that is to produce a laser light, which is a necessary condition, one have to get a stimulated emission. So we need to supply some energy to the electron which is in the excited state. That is, we have to maintain more electron in the excited state than to the ground state. Means we have to maintain N2 should be greater than N1, which is the second necessary condition. That is, we need to maintain the electrons, more electrons in the excited state than in the ground state, by supplying some energy in the excited state. That is, maintaining the condition which is the condition is more number of electron in the excited state. And this process of maintaining the more number of electron in the excited state than in the ground state by supplying some source of supplying some source of energy is known as population inversion. Means population inversion can be achieved with the help of pumping. Pumping means sending electron from the ground state to the excited state. Sending electron from ground state to the excited state. Our main motive is to create or maintain more electron in the excited state to fulfill the necessary condition to have a laser light, to have a stimulated emission. So this process of maintaining the electron is called population inversion. And population inversion, it can be achieved with the help of pumping. Means sending the electron, no need to write at all, sending the electron from ground state to the excited state. So from the Einstein coefficient, we get A21 B21 equals to 8 pi h rho cube by c cube, which is the first Einstein coefficient equation, and B12 by B21, it is the second Einstein coefficient equation. From these two equations, we get two necessary conditions. First is the incident radiation should be high. First condition is the incident radiation should be high. If the incident radiation is high, then as I explained before, that then R will be less, then A21 will be less than B21, means stimulated emission. Our main motive is to have stimulated emission, to have a laser light. So stimulated emission is greater than spontaneous emission, which will fulfill the condition. And the second is, if maintain population inversion. Population inversion means maintaining the more number of electrons in the excited state than in the ground state. In this case, N2 will be greater than N1, which we will get a stimulated emission, which is a necessary condition to produce a laser light. That's all about Einstein coefficient. radiation, and what are the necessary conditions. That's all. Thank you.